Hello everyone, welcome to Swift Algorithm Club. The series was inspired by RayWenderlich Algorithm Club in GitHub. In this segment, we'll cover binary search. You can find complete explanation of binary search in the GitHub repository. So let's get started. What is binary search? Binary search is an algorithm to find an element in a collection of elements. The time complexity of binary search is relatively faster than in linear search, which is log n, whereas n is the size of an array of a collection. So the prerequisite of binary search is the fact that the collection must be sorted beforehand. So let's consider some example. Suppose we have an array of 1, 3, 5, 7, 8, 9, 11, and 15. So we have 8 elements in our array of integers. So when we want to find 1, so we're looking for 1 in this array. So in a binary search, we'll have we'll first divide the array into two halves. So suppose we have two pointers, left and right pointer, and we'll divide the array into two parts. So we get the middle element, which is in our case is 8, because our left pointer is 0 and the right pointer is 7, which is last element, index of last element. So we'll get the middle element, which is 3, and this one will be, the middle will be 7. So we'll get the middle element, which is 7 in our case, and we'll compare it with 1, which is, and 1 and 7 are not same, so we'll move our right pointer to 5, left element from our middle. So, and then in this case we have 1 and 5, so we get the middle, which is 1, which is 3, and compare those 3 with 1. In this case they're not equal, so we'll move right pointer to this position. So our left and right pointer are the same. So we'll get the middle, and 0 plus 0 over 2 is 0, so our middle will be also 0. So we'll compare the middle, which is 1, with our desired value 1, and they are same. So this means that we found the index of 1, which is 0. So the answer will be 0. In case if we could not find the answer, we can return any value, -1 or nil. So basically that's it. The time complexity of binary search is, log n for time, because when we're actually searching for element, we're actually dividing the array into half. So this means that in first we have 8 elements, and then we compare the 4 elements, and then 2 elements, and this means that in order to find elements, we keep dividing our array into 2 parts, and then we completed 3 steps. In the last step we found the answer, so completed 3 steps. This means that the logarithm of 2 base 8 is 3. So, and we can neglect the constant because we're considering upper bound, so you can say that the time complexity will be just log n, and space complexity can vary between log n and 1. For recursive implementation, the space complexity will be log n, and for iterative implementation, the space complexity will be constant. So let's first write an algorithm for recursive approach. So let's get started. So let's define function binary search. So as an input, as a parameter, we'll get array of integers, and we're searching for some number in this array, and we have two positions, starting position and ending position. Again, our array must be sorted. So if our starting position is greater than ending position, this means that we could not find the answer. We cannot find the number in the array. Otherwise, we'll get the middle element. We'll get the middle element, and first we'll compare our middle element with number. If they are same, this means that we found the answer. Otherwise, if our middle element is less than our number, this means that actually our middle element is relatively small, so we need to consider all of the right elements from the middle. So this means we will call binary search on right part. Number, the starting position will be mid plus 1 and will be end. And else, if our middle is greater, then we'll consider the left part. So array number start and right pointer will be mid minus 1. So that's it. Let's create some array of numbers. 1, 3. Actually, we can use our example. And let's find the index of 1. And as parameter we'll pass numbers. We'll want to find 1, and our right pointer will be the last element in the array. So let's print our answer. And let's write it recursive. This is the recursive implementation. So it returned optional 0, so we can get rid of this optional by using some default value. -1 in case if our function return nil. Let's search for index of 7, which is 1, 3. It should be 3. Yeah, and our function now only works for integers. Let's make it generic so so we can use it for doubles and floats and other types. So let's make it generic, and it should also, our generic type should confirm the compiler protocol because we're actually comparing the numbers. So let's change it to generic type. And starting and the point will be integers, so it's integers, and everything will stay the same. 8 or 6 return 3. So that's it. Let's, instead of using the start and end pointer, let's use range. So let's create our range integer, and as in start we use lower bound of a range, lower bound, and as an end we'll use upper bound. So let's just copy paste it everywhere. Start. So in this case we also need to change it to range, so from and there is also this, change it to range. So let's see if it works. Networks, let's search for 11, which is, I guess, is 6. It should return 6. Yeah, let's search for 4, which does not present an array. It should return -1. Yeah, so that's it. That's basically binary search recursive implementation. So thank you for watching. Hopefully in the next video we'll consider the iterative approach of binary search, whereas space complexity is constant.